Okay, welcome to the class, and we have been discussing this DMRS, and we will discuss different structure of DMRS. We will finish discussing it in this class. Okay, again recapture what did we discuss? We discussed this type 1 single symbol DMRS port and how many ports it can be used to define. It can define maximum of 4 orthogonal ports. Okay. And how they are defined, that is what we saw. Okay. So, these ports are given numbers, okay, they are numbered from 1000 to 1003. Okay. So, first 2 orthogonal ports, they use even number of subcarriers, okay, even numbered subcarriers. Okay. Then what are we saying here? They are using the same subcarriers, but they are orthogonal in the code domain. Okay. Then what we say here technically is that these 2 ports belong to CDM group 0. Okay. Then antenna port 1002 and 1003 use odd number subcarriers in the frequency domain. Okay. And then these ports are the orthogonal in frequency and code domain. Together 4 ports, okay, you are using orthogonality in code as well as in frequency domain. Okay. And this single symbol DMRS, it has a clear limitation, okay, that how many ports it can define maximum of 4 ports. Let us say you want to define more number of ports, what do you do? Okay. That is what we are going to see immediately after this, and that is where it comes. Okay. See this. Okay. Right. So, immediately you see this, what have we done? Okay. That we have come from single symbol DMRS to double symbol DMRS. Okay. And what is happening here? Okay. First, there are multiple things which are happening. Okay. You see this length 2 orthogonal code cover and frequency, okay, and length 2 orthogonal code cover and time. If you see that, what were we calling here? Okay. Length 2 orthogonal code cover and frequency. We were not using this additional dimension, okay, to create orthogonality. Okay. Correct. And that is what we are using now, and that is where the notion of the double symbol comes. Okay. And if it's a simple exercise, if with single symbol we can define 4 ports, with double symbol what will be the maximum number of ports you could define if you use similar kind of architecture? It will be 8. Okay. And that is what is happening. Okay. Right. You see this, there are like 8 ports running from 1000 to 1007. Okay. And it is very easy to understand if we have understood the content on the last slide. Okay. So, what are we saying? So, how many different code groups? 4 different code groups, and in the last slide how many different code groups were there? Code group 0 and 1, right. Okay. What does that mean? The code groups, basically they are differentiated using only the codes, that is what it means. Okay. They will be using the same subcarriers. Okay. Correct. So, why are we calling this as this one CDM group 0? Okay, because they are using the same subcarriers. Okay, but they are differentiated using codes. Okay, and what is the code over here? You see this plus plus and plus plus minus minus across these 2. What is happening? They are using, you are differentiating them. So, between these 2 and these 2. Okay, what is happening? They are using the same subcarriers, they are using the different subcarriers. Okay, correct. CDM group 0 and CDM group 1, okay, they are using different subcarriers, that is how they are orthogonal. Correct. Okay. But within these 2, what is happening? They are differentiated by the code. Okay. So, that is why they are in the same code group. Okay. So, they are differentiated by the code. Okay. Now, again we are calling this as same code group, because code group 0 and code group 0, why? Because they are using the same subcarriers. Again they are differentiated using different code. Okay. So, if you see this, they are orthogonal using this code. What is the code? Plus plus minus minus plus minus minus plus. These 4 subcarriers, if you see, okay, plus plus minus minus plus minus plus minus, you do the inner product, it will come out to be 0. Similarly, you do the inner product with this, it will come out to be 0. Similarly, you do the inner product with this, it will come out to be 0. Okay. Right. So, what are we saying here? Code group 0, these two code groups, okay, you are using 4 subcarriers, okay, to create 4 different ports. You will need that. And how are they differentiated? They are differentiating using this orthogonal code cover. But this this code cover, now how are you creating that orthogonality? You are creating that orthogonality in both frequency and time. Okay, this additional dimension, additional symbol has come, which is giving you additional dimension to create another level of orthogonality. With only this, okay, right, with only single symbol, you could not create this. You could not create this code group. That's what we saw in the last slide. Okay, but with additional symbol, you are able to create 2 additional code covers. Okay, right, and that's what is happening. So this code group and this code group, they are using the same subcarriers. Okay, but since you are using 4 subcarriers, you are able to create 4 orthogonal DMRS. Okay, correct, and similar is the case here. Okay, so 4 plus 4, 8 orthogonal DMRS. Okay, so what are we saying here? What is coming out? Okay, if more than 4 orthogonal DMRS ports are needed, 2 consecutive OFDM symbols are used. Correct. Okay, and they will be required. Okay, there are multiple use cases in which you will need more than 4 orthogonal ports. Okay, let's say like user has 4 antennas, okay, and you want to support 4 different layers to that user. Okay, it's a high-end mobile, okay, with 4 receive antennas, and then you will need that 4 orthogonal ports, right? And so here also, so this double symbol has 8 reference signals which are orthogonal in frequency, time, and code. See this. Okay, how are you creating this orthogonality? We are creating it using frequency, time, and these 3 domains we are using to create orthogonality. Okay, time is coming because there is a second symbol, OFDM second symbol. Okay, right. So now what is the limitation here? How many maximum number of ports you can define? 8. Correct. Okay. Now, so you see this from type 1 single symbol to type 1 double symbol, you are moving from 4 to 8. Okay, right. So I will show you type 2 single symbol, wherein you can create maximum of 6 DMRS port. Okay, and you extend the same logic to type 2 double symbol, you will be able to create 12 DMRS orthogonal ports, and that's the maximum. Okay, standard in release 15 define maximum of 12 orthogonal DMRS ports. Okay, it was not felt, the need of defining higher orthogonal port was not felt because you could not transmit so many layers in parallel. It was like people did this rigorous simulations like we do, okay, in our lab, and figured out the system will never see users which will observe more than 12 layer transmission, or multiple users which will observe this kind of channel wherein you can support such high number of layers. Okay, so it is restricted to 12. Okay, the number of orthogonal port is restricted to 12, and that's what I am going to show you. Okay, so what is this? This is type 2 single symbol DMRS. Okay, correct. And what is happening here? Okay, so then let's read through this. Okay, so what are we saying here? First thing is, so each CDM group for type 2 consists of 2 neighboring subcarriers over which a length 2 orthogonal code is used to create 2 orthogonal reference signals. How is it defined? Okay, what are we saying here? Okay, what is the difference between type 1 and type 2? You see this, okay, what are we saying? Plus plus, this is CDM group 2 we have defined. Okay, this is CDM group 0, we are defining 2 orthogonal DMRS. They are defined over same subcarriers. Okay, correct. Look at the difference now. Okay, so this fellow is repeated only after 4 subcarriers. Okay, correct. And so it's okay. So this is one orthogonal group. Okay. Now how is the second group created? You shift this entire thing by 2. Okay, correct. Plus plus and plus minus, but it is shifted by 2. Right. Okay, correct. So how are these 2 DMRS orthogonal? They are orthogonal using the code. Okay, again they are orthogonal using frequency. This is also orthogonal using frequency. Okay, correct, because first 2 are defined here. Okay, then this group is defined on the next 2 subcarriers, but using the same code. Right. Okay, correct. And the third group, if you look at this is shifted by 4. Okay, so this will be shifted by 4, this will be shifted by 4, it will come at the end. It's difficult to show here, okay, but that's what is happening. Okay. So how are you able to create these from 4 to 6? How are you able to move? You have reduced the pilot density. Okay. See this, how many pilots are given to this for this port? Only 4, correct? And in type 1 single symbol, how many port this, how many resource element was given to this port? 6. Now it is 4, right? Okay. So that's the trade-off you will have to make, because if you want to define a higher number of port without increasing the number of resource element you are using for pilots, you basically reduce the pilot density, correct? Okay. So here you look at this, you cannot, so you can interpolate between this and this, but for here this interpolation will not be that great because you don't have any pilots coming over here, but that's how you'll have to live with, right? Okay. So what is the difference between type 1 and type 2 single symbol DMRS? You have created additional DMRS port by reducing the pilot density, that's all. Okay. Instead of giving 4 pilots to each port, instead of giving 6 pilots to each port, which happened in type 1, you are giving 4 pilots to each port. Okay, correct, and that's what is happening. So you are able to create 6 orthogonal pilots. Okay, so let's read this. So that's what I have said. Each CDM group for type 2 consists of 2 neighboring subcarriers over which a length 2 orthogonal code is used to create 2 orthogonal reference signals. You have created 2 orthogonal reference signals, right? Okay. 2 such pairs of subcarriers are used in each resource block for one CDM group. 2 such pairs of subcarriers are used in each resource block. This is one resource block for one CDM group. Fine? Okay. And so with 12 subcarriers in a resource block, we can create 3 CDM group with 2 orthogonal DMRS in one OFDM symbol of resource block. 3 CDM groups, right? Because that's how you have created them. Okay. So so what happens now? I'm not going to show you that figure. Okay. If it is type 2 double symbol, what will happen? 6 will become 12, right? We move from 4 to 8. Here we'll move from 6 to 12, right? Okay. I don't have that figure today. Okay. So maybe sometime later I'll show you. But this is from type 2 single symbol to type 2 double symbol. You will be able to create 12 orthogonal DMRS ports, right? Okay. So these are 2 different kind of structures, type 1 and type 2, which tells you how to create orthogonality in DMRS. Okay. And what is the maximum number of orthogonal DMRS port you can create? Only 12. Okay. Correct. And now, these were the structures. Okay. And I have to tell you a little more about this. Okay. And what is this? So this DMRS resource element, okay, is basically QPSK symbol. Okay. Right. So what is happening here? Let's look at this. Okay. So you take the DMRS, okay, then you modulate them using QPSK, okay, then do this orthogonal code cover. Okay. Underneath this, each one of them is QPSK modulated. Okay. Right. So and this is on top of that, you do the orthogonal cover, and now I'll have to tell you how this QPSK modulation is done. Okay. So each DMRS resource element is QPSK modulated, which is generated as follows. Okay. So this is how it is. Okay. R is basically the DMRS sequence. What is happening? Okay. What is this? There is some code. Okay. C. Okay. So it will be between 0 and 1. Okay. The pseudo random length 31 gold sequence. And what is this? You recall scrambler. Okay. You generate this code using scrambler. Okay. We studied that in detail. So scrambler use is not limited only to generating code for a scrambler, it generates code for this for the DMRS also. By this code, this is different from that orthogonal code cover which we just discussed. Okay. So this is for generating this QPSK modulation. Okay. And what is this? This sequence which generates this gold sequence, okay, is initialized with a different seed value for each OFDM symbol of a slot. Okay. So you generate this sequence C, okay, which is a function of each OFDM symbol. Okay. And okay, so what happens here is you remember that when like we were generating, how were we like initializing that? You had to initialize the scrambler, correct? Okay, right, with 2 different input values. Okay, and in this case, okay, that initialization function is a function of each OFDM symbol. That is what this bullet is telling. I am not going to go into the details of this to define this, that how this code is generated. Okay, fine. Okay, this is for the QPSK modulation of the DMRS. Okay, fine. Now, once you have generated this sequence, how do you do that orthogonal code cover? That is what I am going to tell you. Okay, so hang on. Okay, so that is this reference symbols which are QPSK modulated. Okay. By the way, so this sequence is known to the both transmitter and receiver. That is why it is pilot. Correct? Okay. Right. So this is first. This is the base data. Okay. QPSK. Now after that, they are multiplied with this orthogonal code cover sequences, and this is from this part of the standard. Okay. So what is happening over here? I will show you this, the formula. Okay, and I will discuss this in detail. Okay. So what is this? What is this constant which is coming over here? What is this? Beta DMRS PDSCH. Okay, this is the amplification factor. It is basically how much you want to amplify the pilots. Okay, with respect to data. Okay, so what is typically done is that you could basically you could allocate more power to the pilots when compared with data. Okay, if the UE is operating in a bad channel condition, okay, is a poor SNR. Okay, so its channel estimates are going to be poor. Okay, so a smart way to handle this situation is that allocate more power to the pilots, so that at least your channel estimates are good. Okay, if channel estimates themselves are bad, it will affect the rest of the performance of the rest of the chain. Okay, correct. So this is basically the amplification factor which is used to amplify the pilots with respect to the data. Okay, correct. And now you see that there are multiple variables which are coming over here. This is slightly on a smaller side. Okay, I'll discuss this in detail also. Okay, so this L dash, okay, because you have to generate this orthogonal code cover, right, for both single symbol and double symbol. Okay, so this variable L dash, okay, which is, you see this is coming over here, L dash, okay, is 0 for single symbol and it runs from 0 to 1 for double symbol DMRS. Okay, and what are this WF and WL? Okay, right, WF and WL are the codes. Okay, and a part of the codes. Okay, that's how they are defined. Okay, so this is for type 1. Okay, right. So what is happening over here? How many maximum port? 8 ports. Okay, correct. And so how many groups? CDM group 0, CDM group 1, CDM group 0, CDM group 1. Okay, right. This delta is an offset which is coming over here. Okay, I'll tell you how each one of that is used. Okay, so these are the codes, +1, +1, +1, -1. These are the codes. So you see this R is this sequence. Okay, which is what is this? This is the QPSK modulated DMRS. Okay, and what is happening after that? You are using WF and WL to create that orthogonal code cover. Okay, I'll give you an example, but let's see this over here. What is happening? WF is defined over here. Okay, for two different indices, K dash, and K dash is equal to 0 and K dash is equal to 1. Okay, and this is also defined for two different indices, L dash is equal to 0 and L dash is equal to 1. Okay, this is a table which is defined in the standard. We use this table to generate this code cover. Okay, right, and I'll have to see, there's only 2 minutes left. Can I go to the next slide? Okay, so I'll try doing it here, or I think so. I'll stop here. Okay, this will do this exercise. It will require me some 5-10 minutes to do that. Okay, so what are we saying here? Just to summarize, that this expression, okay, with the help of this expression, first one we understand in detail. Okay, these are two orthogonal covers. These sequences are used to generate the orthogonal code covers. Okay, right, and this is the base sequence. Fine. Okay, and this is the QPSK modulated sequence, DMRS sequence, which is used. Okay, On top of that, you are using this WF and WL to basically create that orthogonal chord cover. I will take an example, it will become extremely clear how this is basically how product of these two is used to create that length 2 sequence or length 4 sequence which we have seen. Okay. So, I will stop here, I will continue this in the next class. Okay. Thank you.